Maybe I hid it.
Where is it? It's okay.
I really,
It's okay.
this is so, I'm sorry.
You can just go back to like presenting. It's fine.
Okay. Okay, cool. Yep, sure.
All right, hi everyone. Welcome to the last seminar of the summer. So today we are very happy to have Jacob, who is our postdoc here with Gautam and Shi. And Jacob has what your PhD from UCSD?
Yes.
Okay. Jacob got his PhD from UCSD and has been doing a postdoc at Copenhagen and now here. Copenhagen, Rasmus.
Yes, yes.
Good. Okay. Sorry, I'm a bit out of it, but
No problem.
and it works a lot on differential privacy and distributed learning. Today he's going to tell us private optimization. Cool.
Okay, thanks for the introduction, Sefer. And my talk today is called Lower Bounds for Private Optimization via Reconstruction Attacks. And this is work with my collaborators from University of Copenhagen, Rasmus and Lucas. So I'm going to be talking about graph privacy a lot today. And the motivation is that graph data sets are everywhere. Graph data sets can come from a social network where you have interactions between users. It could also be traffic on roads or internet traffic. Or it could be bipartite graphs where you have a set of users, a set of items, and edges form when a user likes an item. And to define differential privacy, you have to follow these graph semantics. So in differential privacy, we talk about adjacent graphs, which are two graphs where the data of a single user is added or removed. So depending on the semantics of that graph, the adjacency notion can be really different. In a social graph, this gives rise to something resembling node differential privacy because a user is a node, and you might want to hide the friends of that entire user. In a graph that arises from traffic, usually the users are interacting somehow with the edges. So an adjacent graph would be one that has a bounded change in the edges. And then you can also, in a more structured graph like a bipartite graph, you might need a different notion of differential privacy where the set of things that you like is a public thing, but then the nodes are private and you want to hide things that a user liked. So these three examples just show that it's an interesting problem to even just think about what does privacy mean for graphs, and it, in my opinion, hasn't been completely resolved yet. But today I'm going to focus on edge weight differential privacy. So we're going to be focusing on like graphs where the edges contain the private information. So think of it as like a road network. And in this setup, we have a public road topology given by vertices and edges, and private weights that are assignments of real numbers to the edges. And for this, it's mostly going to assume that they're non-negative edge weights, just so our algorithms work. And one user is going to produce a bounded weight change to the weight vector W. And we measure this change by the L1 distance. So we say that two weight vectors, W and W prime, are adjacent if their L1 distance is less than 1. And so just as a reminder, the topology itself, so the edges without the weights, is public. And we can actually adaptively design algorithms on this topology, but the weight vector is private. So I've drawn two examples here in the slide. So we changed the red numbers in L1 distance by at most 1. So formally, edge weight differential privacy, you have two graphs given by VE and W and then VEW prime. They're adjacent when their weight vectors differ in L1 norm at most 1, and we can replace the 1 with any small constant. It's just trying to capture what a user might do to the weights. And we say that an algorithm is epsilon delta edge weight differential privacy if for every adjacent graphs with that notion of adjacency, The probability distribution of A of G and A of G prime is almost the same. And we measure the closeness in probability distribution with this funny differential privacy way of doing it, which says that the probability of observing any event, whether you have G or G prime, or any event set rather, it is roughly the same up to this e to the epsilon multiplicative factor and a delta additive factor. And informally, it's saying that any L1 change to the edge weights is protected, at least when epsilon and delta are small. So this is the definition we'll be using. And our main ingredient is going to be reconstruction attacks. So we're going to be studying problems from mostly the lower bound side. And a really nice way to prove lower bounds in differential privacy is to use reconstruction attacks. So in this setup, a reconstruction attack doesn't actually apply to a graph data set. So part of our insight is how do we get these things to apply to graphs? For a standard reconstruction attack, you have some data set X, and it's just like a tabular data set, could be like binary values. And there's an analyst who outputs some information about X, so it's given to an output Y. And then this output Y falls into to make it sort of an attack type of thing, the output Y can be post-processed by an attacker who tries to reconstruct X. So they try and form a vector X prime. And the bottleneck of this setup is that X prime will still be differentially private because of post-processing. So differential privacy, one of its important properties is that you can post-process any output that satisfies differential privacy. So even when you're forming your guess vector X prime, the X prime is differentially private. So X prime has a bottleneck. And so the reconstruction attack from this setup is that you can actually just view this process that guesses X prime given X as a differentially private algorithm itself. So if you have some data set X, and for now we're going to have a binary data set, if X is drawn uniformly from 0, 1 to the n, and it helps to add randomness to X just so this result is cleaner. So you have a random binary data set, and an algorithm A of X tries to guess X prime and outputs X prime, but it satisfies epsilon delta differential privacy. Then we know that it can't be correct much more than half the time, or its error has to be roughly n over 2. And the exact constant is this 1 minus delta over 1 plus e to the epsilon times n. When epsilon and delta are really small, then this is really close to a half, and it's what we would expect. If the algorithm were able to pinpoint and say, with 80% accuracy, I know I'm able to get all of these endpoints correct, or I can get all of the endpoints correct with 80% accuracy, but my prior was 50% accuracy, then that wouldn't be private. So that was the simplest reconstruction attack. And there's two more, slightly more generalizations of this that we're going to use for our graph lower bounds. In the second one, we're going to consider a data set that is not binary, but it's drawn from a data universe K of size K. In that setting, the Hamming distance between X and X prime is going to be, if you were randomly guessing, it would be 1 minus 1 over K times n. And here it's 1 minus e to the epsilon over K minus delta times n. So that's really close to 1 minus 1 over K when epsilon and delta are small. And then lastly, we're going to also consider attacks that don't try to reconstruct the entire data set, but rather they take a data set and then they output a set of indices. So that's the first output in 0, 1 to the n. And then it also outputs a guess just for those indices that it is trying to reconstruct. So basically this attack is saying, based on the output, I'm not confident about many of the points, but for a small subset of the points, I'm confident and I can guess them. So the reconstruction lower bound we have here is that if you try and reconstruct I points, then the Hamming distance between your guess is going to be at least, and then we have the same constant roughly, 1/2 times the expected size of the set you're trying to reconstruct. Capital I is the index set output by your algorithm. It's the set that it is trying to reconstruct, and it's a subset of n. So I kind of encoded that as 0, 1 to the n. Does that make sense?
Why itself is a random variable.
Yeah, so I itself is actually a differentially private output. So that, yeah.
Is it n-dimensional vector?
You can think of it as you can think of it as a subset of n of the index set 1 to n, because it's really just trying to give you an index set where it's confident that it's seeing data it can reconstruct.
Did you tell us at someone how any of these are programmed or not?
In my next slide, I'm going to show you the first one, and the next two are generalizations. The third one is a little bit messy, but it's still the same spirit. No, you just have to sum over a bunch of things. The first one is easy because it actually follows from, so we're going to prove the one-dimensional case of the first lemma. So let x be just a bit uniformly drawn from 0, 1. If A is differentially private, then if you try and guess x, your success rate is going to be 1 minus delta over 1 plus e to the epsilon, or your failure rate rather. And because we're in a symmetric setting, x is uniformly drawn from 0, 1 to the n, you can kind of just show that the worst case algorithm is a binary symmetric channel with flipping probability p. And the maximum or the lowest possible value of p that you can have while satisfying epsilon delta differential privacy is exactly that constant. P equals 1 minus delta over 1 plus e to the epsilon. And that comes from just rearranging the definition of dp. And actually, the general case follows coordinate-wise. So you can use linearity of expectation on each coordinate, and then you can just condition the algorithm on that particular coordinate and apply the one-dimensional case n times. So the n-dimensional case is this constant times n. So that's exactly where it's coming from. And then you can generalize this pretty easily to a larger domain in the one-dimensional setting, or a one-dimensional data set with a large domain. And that's how you'll get the first generalization on the last slide. So that proof is just a different channel. And then this subset reconstruction attack is a little bit more involved, but you have to sum, you can't just condition on one coordinate each n times. You have to sum over all 2 to the n possible outputs, but it really is the same spirit as this one-dimensional case. So any questions about that?
Which paper? This is S16.
Sealfon 2016, but it has also been proved before that. There's this paper by Day from 2012, a Ninja Day.
Yeah. This was the Adams paper on graph shortest path or something.
Actually, that Day paper only considers reconstruction lower bounds.
Right,
and
the Sealfon paper. Right?
Oh yeah, the Sealfon paper is shortest path. Yeah. So we're building off of their work a lot.
For this bound, you use there was a lemma when studying by the answer rational. It says that if you have a pair of neighboring data that you cannot be accurate on both for input. And this for this 0, 1, and it feels like maybe you can use that. And probably you can get very similar inequality values because you have only 2 input, right?
Yeah, only 2 input. Yeah.
Just you flip that bit, and then the lemma tells you cannot guess the correctly for both cases.
Like you think this could be a pattern lower bound?
Yeah, something like that.
Awesome.
You're saying you can obtain the same lower bound using this strategy?
Whether the input is 0 or 1, you cannot be accurate simultaneously.
Yeah.
That means that you must
Okay.
make a mistake in guessing the true value.
I think that is like a similar type proof, right? Like applying the definition of dp in a symmetric way. Interesting. Well, we might have to talk about that more offline. Okay, so this edge weight DP model has a lot of interesting algorithms and lower bounds. So I just want to paint a quick picture of what's been going on here. So you can study a lot of combinatorial graph questions, and the bounds that I have here, they reflect additive errors. So the expected cost of your differentially private algorithm in trying to compute some combinatorial thing minus the optimal cost. And you would consider the worst case overall weight vectors of this quantity. So the all pair shortest paths problem, that was, there's this paper by Sealfon from 2016, and it's been improved. And that has some interesting algorithm design. And we know that you can compute all pair shortest paths with like root n over epsilon error. And there's a matching polynomial, well, it's not matching, but it's a polynomial lower bound, which uses some really interesting combinatorial graph families. And I'm kind of writing down this hard topology, which is the family of graphs that they use to show their lower bounds here, because well, this is something that I'm gonna elaborate on later. So you can come up with like a sparse family of hard graphs where like random weight vectors are going to have to incur some error, like the n to the 1/6 error. And then the minimum spanning tree problem, there's an upper bound of like n log n over epsilon. You can actually sharpen it to n log m over n, where m is the number of edges. And the lower bound is linear. Then there is a paper that studies the minimum spanning tree problem under a different type of adjacency. So this is just trying to highlight that you don't actually even have to use L1 change to the vectors. You can actually use an L infinity if that makes more sense. Like if somebody took a ride on every single road in a day and you want to hide that. The lower bounds here are like tight. I didn't write down the log factors, but it's n to the 3/2 over epsilon and omega n to the 3/2 over epsilon. And then the minimum weight perfect matching problem is actually for differential privacy. It's quite similar to the minimum spanning tree problem, and actually the same bounds are known. And finally, hierarchical clustering, and that's like a recursive clustering algorithm that I'm gonna define that later. There are some algorithms known that there's a nice cost function that I'll also define later. So there's a lower bound of omega n to n squared over epsilon, and an upper bound that matches that up to log factors, but it takes exponential time. So sometimes that happens in differential privacy, where you have an exponential time algorithm and a polynomial time algorithm that has worse error of n to the 2.5 divided by epsilon.
Mostly PE algorithms, are they mostly following the time?
For which problem? Oh,
It's nearly, at least the P25.
I think that these algorithms, the all pair shortest path problem. Okay, so all of these algorithms, except for the exponential time one, are polynomial time. And many of them satisfy pure differential privacy. I didn't differentiate them in the table. And one case where I know where pure differential privacy is definitely doing worse than a prox DP is for the all pair shortest paths problem. So this bound is actually only works for a prox DP. If you have pure DP, you get like the n root n becomes like n to the 2/3 or something. Does that answer your question? Okay. Okay, so looking at this table, what did we improve? So now I'm going to get into what did I improve in this table. So it's an interesting question to see which of these lower bounds and upper bounds are tight. So I proved stronger lower bounds for the minimum spanning tree and well, it wasn't just me, it was me and my collaborators, and for the minimum weight perfect matching. And then also some of these topologies are a little bit too worst case. So the topologies that were used to prove the lower bounds, one could view these as a little bit too worst case, especially if you're using like the complete graph. You're basically saying if somebody has a complete topology, then I can embed weight vectors in there and confuse a differential privacy algorithm. But in this model, the topology is public and it is usually a graph, like it's supposed to be a graph that you would encounter in in real life. And so you're not going to get the complete graph always. Usually, you might get a sparse graph, or yeah, like you're probably going to get some graph that's much more sparse than the complete topology. So it's an interesting question to see if these lower bounds actually generalize to graphs that are sort of not worst case, like not the complete graph, and perhaps can we actually come up with lower bounds that apply that are sensitive to the topology? Like if you give me a topology, then I can compute you the strongest possible lower bound. So we made a step in that direction by showing lower bounds for not the complete graph for the hierarchical clustering problem. Okay, so I will now get on to the minimum spanning tree results. So let's get into what was known before, just illustrate it. So let's consider a graph that's like a double star graph. It has 2n edges, and I guess it would have maybe 2n minus 2 edges, actually, if you have n vertices. There's a central vertex, and it's attached to every vertex on the perimeter by two edges. So it's doubly attached. Now we're going to encode a random binary data set into each of the edges. So for vertex I, we take the data point xi, and in one of the edges, which is fixed, so let's say edge number 1 that goes to the vertex, we encode xi. To the other edge, we encode 1 minus xi. So every edge is going to have a 0 or a 1, and it's going to be flipped depending on whether it's in the data set, or whether it's a 0 or 1 in the actual data set. Now, when we release a minimum spanning tree of this graph, it contains a lot of information about the data set. So the output, so we're computing a private minimum spanning tree on this input graph. And now we're going to come up with a attack here. So you can think of the attacker as sort of a decoder. We want to decode the input data set. And so the attacker knows how this is like, they kind of know how the algorithm works. They just don't know the data. So they know how the algorithm would have encoded the data set. And so the attacker just says, I was given a low-cost minimum spanning tree. So if the minimum spanning tree preferred one edge over the other edge, then I know if it should be a 0 or a 1 most of the time. So you can come up with this decoding lemma that says, the number of errors this decoder is going to make is at most the weight that the tree pays. And furthermore, this x prime, it only accesses the data through the private tree. So it satisfies 2 epsilon 2 delta differential privacy in x. So when I flip a bit of x, the weight vector changes in L1 distance at most 2. So you have 2 epsilon 2 delta. So a corollary of this is that any edge weight differential privacy algorithm, like the minimum spanning tree one, it has to have error that is at least this constant that we saw from the reconstruction attack, 1 minus delta over 1 plus e to the epsilon n. For constant epsilon and delta, this is linear. So we've just shown that there's a linear lower bound. Otherwise, by this decoding lemma, you would reconstruct too much of the data set. And now I didn't show you how to get the lower bound for epsilon going to 0. So to get a lower bound of omega n over epsilon, but you can do the same construction and you just encode 0. You just blow up the weights a little bit. It's not too different.
Question here, sorry.
Yeah.
You have like a multi-graph, but I guess I should get too hung up on that and probably replace it with a slightly different gadget if you wanted to.
A single. Yeah, I think you could blow up. You could just have 2 additional vertices for each of these each double edge, and just put each double edge onto its own additional vertex.
Yeah.
Like a bunch of diamonds.
Like that middle thing that you have the 0 and 2 vertices and just connect them. And then everybody.
Oh, yeah. Yeah, two central spokes.
Sure.
That's a nice one too.
Yeah. Definitely.
True. Okay, so that established a linear lower bound. So now let's get into our first result, which is a tight lower bound, a stronger lower bound. So we're going to consider a different graph. It's going to be a complete bipartite graph, n edges on both of the left and the right vertices. And we're inserting an additional path into the right vertices. So it's like a bipartite graph plus a path. Now we're going to encode the data set by just taking every point. So we have a bigger domain now. We have points in n to the n. And we take a point and we put it on the left vertex. So point I is going to get vertex Li in the left side. And we're going to pick exactly one, or all of the edges are going to be, they're going to have weight C, except for the one that is going to the data point that we want. So if that data point has value j, then we map it to, we make sure that the edge from I to j has weight 0. I think it's actually reversed. It's reversed here. So here's this example. If you had a data set where the first element is 2, then L1 is going to have weight 0 to R2, and it's going to have weight C for some constant C for all of the other edges. So the yellow edges here have weight 0, the gray edges have weight C. And finally, the path is going to have weight 0 as well. And now we're going to release a minimum spanning tree on this graph.
So just to understand your goal, you're going to try to prove something with a loss factor as well? Is that...
Yeah. So in order to do that, we need to use that more general reconstruction attack lower bound. So what does the decoder do? The decoder receives a minimum spanning tree. And what we know for sure is that every edge on the left, or every vertex on the left has at least one edge on the right. So if it has exactly one edge on the right, we're going to guess whatever vertex it got mapped to on the right. If it has more than one edge, we'll just have a question mark. So in this example, the second L2 gets mapped to 2 edges, or to 2 things on the right, and we're just going to have a question mark. We're going to say, I don't know.
When you output an MST, you're actually not outputting the tree. Yes. What does
Oh, you are outputting a tree. To what? Oh, because there's an additional path. There's an additional path on the right. It doesn't have to pick them.
Really? You just can multiply every other edge with weight n.
Mm-hmm.
Then if you don't pick even one of those edges, I mean, if it works this way, it works well. If those edges have weight 1, for instance, and every other edge has weight more than n,
Yeah.
or n.
Are you saying the edges in the path?
Yeah. Exactly.
Okay. Yeah.
Then if you do not pick even one of them, your MST is going to get.
Yes. Yes.
Sorry, no, this one. I don't. But it's fine.
Okay.
I'm sure there should be a gadget you can put there that mesh to force that you're picking things from the right side is a connected component, but
I see.
that is fine.
I see. So the lemma that we can prove is that if we encoded a graph in this way into the weights of a bipartite graph, then for any spanning tree that was possibly returned, we attempted to decode that. And we know the Hamming distance of the decoding is at most the additive error of this tree. So the weight of the tree minus the weight of the optimal tree divided by the C. C is how much is the factor that we blew up the weights. And the proof of this is, well, show that the optimal tree has weight 0, which we can do because you can just take the matching plus the path. So that's what the path is there for. All of those edges have weight 0. Now for every vertex on the left, consider its right neighbors. You know that there's at least one right neighbor. And the Hamming distance is just summing over whether the right neighbors is literally a singleton set containing the correct right neighbor, but that is undercounted by the weight because the weight is the size of the number of right neighbors minus the correct neighbor. So the indicator is less than the size of the set. So it's undercounted. And you can show that the total weight will just be the weight of the tree divided by C. So a corollary is that if you use the minimum spanning tree algorithm with additive error alpha, then when you decode, your reconstruction error of x prime in terms of that Hamming distance will be alpha divided by C. So to summarize our generalized reconstruction attack, we had a bipartite graph, we encoded it by sort of mapping one-to-one, or not one-to-one, but just representing it, the data set. The decoder used a minimum spanning tree and used the vertices it was mapped to. And now we get into the contradiction part. So suppose that minimum spanning tree algorithm is epsilon delta edge weight differential privacy, and it has an additive error of alpha. Then the X that was decoded, this satisfies, now we have to use group privacy because we blew up the weights by a factor of C. And so we need to use group privacy 2C times. And group privacy is I don't know if everyone understood. I didn't explain that, but like if dataset X1 and dataset X2 have differential privacy, dataset X2 and dataset X3 have differential privacy, then dataset X1 and dataset X3 have differential privacy where you blow up epsilon and delta by roughly 2. So we need to use this property 2C times. And so the differential privacy guarantee on the reconstructed vector or the reconstructed dataset X prime is 2C epsilon, 2C e to the 2C epsilon delta. So usually this delta term is still really small because delta is usually less than 1 over n. And the reconstruction error is going to be alpha over C. We saw that in the last slide. So now we finally pick this number C. It's going to be log n over epsilon. And this will give us an algorithm which satisfies log n differential privacy and like n squared delta, log n squared delta differential privacy. And its reconstruction error is alpha epsilon over log n. And that now it's just a contradiction of what that reconstruction lower bound said. Because with epsilon taken to be log n, you still are not you're not able to reconstruct a data set drawn from n to the n with, you must have linear error. So we know the reconstruction error has to be omega n. And so we have a contradiction as long as alpha is less than this n log n over epsilon.
Would that be interesting to reduce this just so that it's from 0, 1 to the n version? Don't have to deal with the extra complexity or not?
But we don't know how to do that and have the n log n. We want to have an n log n lower bound. So that's why we had to do it this way. So it's a more complex construction, but we proved a stronger lower bound. Is that answering your question?
No, but on its own, it would have been nice if it could have been reduced to that or not. Doesn't matter. Like, does simplicity matter? Yeah, not really.
Simplicity of what?
The construction.
Oh, I would say that simplicity of the construction is something that we hadn't really considered for this model before. Yeah, so you could say that this construction is not like it's using the complete graph. So I wanted to try to not use that. So our later results were not going to use the complete graph. So this is an example of maybe a most complex construction that gives you the tight lower bound.
Sorry, one more question. Where did this log come from? Like, it just feels like a little bit magical that it popped out here. You have intuition as to how it caused the log to.
Good question.
Another potentially different way of asking the same question could be like, why did you take C to be this value? Like, if you took it large.
Log, yeah, we took it log.
Would that have been worse? Like,
If we had taken a larger value?
yeah, like, what would it go wrong? Clearly, there's a sweet spot of some sort.
Yeah. So a larger C, the reconstruction lower bound would say, hey, you can reconstruct a lot. I should have put that bound here. Let me go back. So the second lower bound has a 1 minus e to the epsilon over n. We're using n now, minus delta. So it's saying you can take epsilon up to log n, and you're going to get a linear lower bound. And actually, if you take epsilon like a constant, then you're like extremely close to, well, what am I trying to say? Then your error is like if
all but a constant number of them, as you said, epsilon to be a constant, right?
Yeah. So somehow,
right, it's sort of counted that you're reconstructing a constant fraction rather than like none of it or all of it.
Yeah, maybe it's the constant. Yeah, it's the constant fraction regime that is the most, the best for us to use or something. Yeah. Okay, so that's the first result.
Oh.
Oh,
What is that login?
so we said that the minimum spanning tree has additive error alpha, and then we showed that you need to take alpha sufficiently high.
No, I guess that was my question. That's an additive fact.
Yeah, additive, yeah.
Do you know a lower bound for like 1.5 multiplicative plus additive?
Oh, no, that could be an interesting question. Yeah. I feel like we haven't studied multiplicative and additive lower bounds in differential privacy like that much, and kind of an interesting, especially for like graph problems.
The definition is, I mean, it's somewhere else, but
Yes, the definition is multiplicative, but almost always you're adding noise, which satisfies the definition, but like the noise addition oftentimes gives additive error.
But for MST, additive weight is a bit of a weird thing, because if my weights are super high, shouldn't it depend on the magnitude of the weights?
Yes, there is. That's true. So this construction, all of the weights have weight C, which is like log n. So you can have you only need maximum weight of log n over epsilon, and you can show that the error is additive. It has that additive form. If you tried to convert that to multiplicative error, it would be like terrible. It would be like maybe polynomial multiplicative error. But if you allow yourself to have huge weights, then actually the additive gets absorbed by the multiplicative.
I will say that there is one problem where they do a multiplicative and an additive on graph problem, which is like DT synthetic graphs that's called. Like, you want to release the differentially private graph, which approximates the original in terms of like cut values or spectral values. There's been studied both additive but also like multiplicative plus some additive error. You can do a lot better there. But
yeah, so I'm coming from Imola, where people are talking about differential privacy on the graph side, and there everything was like multiplicative.
Right. I think that's sort of a more recent trend. Who gave the talk?
That's the question. So, no, change.
I see. Yeah, I think her paper is sort of one which does that regime, but it's sort of more a subsequent advancement where people get the right answer for the additive one and then multiplicative plus and additive. So I think we'll recall next after this work.
Yeah. Okay, so now I'm going to show a different flavor of lower bound for minimum spanning tree. So we can actually come up with a minimum spanning tree lower bound that is kind of topology aware. So you'll know what that means once I'm done introducing this. So we're flipping the lower bound method. We're saying, let's suppose I'm given a topology with there's no gadgets initially. We don't have like a topology that's going to allow us to design gadgets. We're just given a topology VE, and now we want to apply the reconstruction lower bound. So let's just take a random data set and just throw it into the edge weights. So kind of on a really high level, we need there to be a cheap minimum spanning tree in order to convert additive error into a reconstruction error. And we also need a way to decode the tree that is given when we run the MST algorithm. We want a decoder that reveals a lot of zeros. So the question is, like, when is there enough structure in the topology that will guarantee these two things? And I just drew a topology and showed, okay, we're going to just put zeros and ones on the weights at random. So the structural assumption we need about the topology is it's sufficient to assume that the min cut of the graph is at least polylog or like 5 log n, so a constant times log n. If we do that, then by coloring each edge randomly 0 or 1 with probability 50%, with high probability, every single cut is going to have a 0 edge crossing it. And this will guarantee that there exists a minimum spanning tree of weight 0 in the graph. And the proof is using a union bound. So the probability of a cut ST failing is 2 to the minus epsilon times the number of edges crossing S to T. And you might say, hey, there's exponentially many cuts. So how will this union bound work? But there's a nice result, a classic result from Karger 93, that actually there's only polynomially many cuts that are close to the min cut. And the min cuts are exactly where this is the hardest, because the exponential is going to be the smallest there. So we have there's only n to the 2 alpha cuts of weight alpha times 5 log n, because 5 log n is our min cut. So there's the union bound failure probability. You can just sum over the cut sizes. It's a sum of a polynomial times a inverse exponential. The inverse exponential will win. So you can show that there's a high probability bound of failure. So like 2 over n when you sum all this out. So if you assume that the topology has a min cut of 5 log n, there will be a minimum spanning tree of weight 0 with high probability from this encoding scheme. So that's the first thing we needed. And the second thing we need now is a decoder. So the decoder sees a minimum spanning tree and says, I know that this minimum spanning tree has low additive error. So I'm going to just take all of the points in the data set that were mapped into these edges and just guess that there's 0. So it's a simple decoder. And this will give us the desired contradiction if we view this as a subset reconstruction attack. So observe that the edges in the data, or the data set itself, got mapped to any possible edge in this, or to all the edges in this graph. But only the green edges are going to be guessed. We're only going to make a guess about the green edges. We're going to say outside, we don't know. We're not going to guess 0 or 1. Inside the green edges, because you have a small minimum, the minimum spanning tree is not too high, we know that it's mostly zeros in those edges. So the contradiction comes from if you assume that you have like epsilon equals 0.1 edge weight differential privacy, and the MST algorithm has 0.1 n additive error, so much less than n over 2, then the output, the decoded set X prime, satisfies differential privacy, but the Hamming distance inside of the set I is going to be less than the additive error of 0.1 n. And this is, but it's always going to make n guesses because there's n minus 1 edges in the spanning tree. So that is way less than the size of the output, or the size of the index set. So it's like 0.1 times the expected size of the index set. And that's an exact contradiction of the reconstruction lower bound. And then using group privacy, we can strengthen this linear lower bound to like 0.1 n over epsilon. Okay. So just to summarize what we have so far, we have 2 types of lower bounds for the minimum spanning tree problem. one of the lower bounds applies to a complete graph, and we can actually generalize it somewhat to a bipartite graph with two different sizes or two different sized left and right vertices, and we can obtain the exact upper bound. So the omega n log m over n over epsilon using that bipartite graph construction. Or we can say that if you give me any topology at all that has 5 log n min cut, then the lower bound is still going to be linear. And these two techniques both apply to the minimum weight perfect matching problem. Or no, so the bipartite construction also applies to the minimum weight perfect matching problem. And I'm not sure how to prove a similar result for any topology so that for the minimum weight perfect matching problem. And does that all make sense? I'm going to get into one last problem now, one last problem on graphs. Okay. So now we're going to shift focus quite a bit and talk about hierarchical clustering. So in the hierarchical clustering problem, you have an input weighted graph, and the weights measure similarity. So higher weights mean that these two nodes are more similar. And we want to cluster the vertices based on the weights recursively until every node is in its own cluster. So you'll make a high-level cluster, a bi-clustering at first, and then you're going to look at each of the two partitions and cluster those based on similarity. So it might be something like if you have cities, then the weights on the graph measure like the amount of traffic, and that makes the cities more similar somehow. So that might be how you would, or why you would use this algorithm in real life. And it's represented, you can represent this as a binary tree, and it's also called a dendrogram. So I've drawn two trees here. There's two different ways of clustering the input graph. And the first tree, it first separates A and B from C and D. And the second tree first separates A and D from B and C. And we should prefer the first tree. So I drew two trees to show that not all of them are going to be good clusters. And why should we prefer the first tree? Because it cuts the edges of weight 3, 2, and 5, which is much less weight than what the other tree makes on its highest level cut. So that's kind of the optimization question, is we want to cut the low weight edges with our highest level cuts. So there's a really nice paper by Dasgupta where he made this problem quantitative, like quantitatively, which tree should I prefer? We do this with a cost function, and the cost function does exactly what we did in the last slide. It rewards a tree for splitting higher weight edges later. And so it measures the cost of a tree by summing over all the edges, and then you take the weight of that edge and you multiply it by the height in the tree where it's not quite the height. You take the least common ancestor of the two vertices in the tree, and you compute how many edges are in that, or how many nodes are in the subtree. So for the highest level split, this value is exactly n for all of those edges. So those edges are all getting charged n, which is the most you can charge. So you're multiplying the edge weight times the cluster size at separation. That's what this least common ancestor thing does. So for an example, if we go back to that example graph and we considered how much is edge AB being charged, you would consider the least common ancestor of A and B in the tree. You would see that there's only two vertices when they were cut, and so they're going to be charged 2. So that edge will cost 8 times 2. And so in the first paper, Dasgupta showed that if you just recursively do a sparse cut on the algorithm or an approximation of it, which makes a lot of sense, that's a log n multiplicative approximation to this cost function. And then some private algorithms, I showed them in the table earlier. O of n squared log n over epsilon additive error if you allow yourself an inefficient algorithm, or n to the 2.5 log n over epsilon additive plus a log n multiplicative error if you want polynomial time. And also so we're focusing on the lower bound. So the lower bound shows that the exponential time algorithm is optimal up to log factors, but it applies to the complete topology only. So we want to try and generalize that. And that lower bound uses what's called packing in differential privacy. And you basically need exponentially many weight functions, which are going to encode disjoint 5 cycles. That's going to be your hard family of weights. And you need an additional property that no hierarchical clustering tree will cluster any more than one weight function well. And this is unclear. So it's unclear if this technique can generalize past the complete topology. Because every one of the weight functions in this class is going to use all of the edges. Or not all of the edges, but if you take the union, then you have to use all the edges in the graph. And it also only applies to pure differential privacy. So we wanted to improve both of these things. Go to approximate DP and generalize past the complete graph. So now let's take what we did for the minimum spanning tree and apply it here. Apply the same method. So given a topology, let's assign a random data set to the weights. And we need a cheap hierarchical clustering to exist. And we also need a decoder that will reveal a lot of zeros given a cheap hierarchical clustering. And the first observation is that it no longer suffices to just throw the edges into the graph at random, because that will give the optimal hierarchical clustering will be expensive. It'll be like already NQ, or it'll be really close. It's not going to be low enough. But we can sparsify this. So we're going to assume that the topology is d-regular, and you can assume it's close to being d-regular, like a maximum degree that is for now, let's assume it's d-regular, I think, and you can generalize it a little bit, but we do need to assume that. And we're going to use a sparse encoding of a data set. So the way our encoding is going to work is we downsample the edges with probability 1 over 2D, and then we're only going to encode the data set on the sampled edges. So only on these red edges are we going to encode 0 or 1. And now you can show that with this downsampling, every connected component in the graph has size log n. So clustering a bunch of connected components of size log n is very cheap. It's just n over log n times log squared of n. And so the clustering cost of this embedding of this encoding is going to be n log n. So that is enough to give us a cheap hierarchical clustering. And now how are we going to decode? So here we use a lemma about hierarchical clustering. If you're given a hierarchical clustering tree, you can actually compute a balanced cut A and B. So a balanced cut has n over 3 vertices in both of the cut partitions, such that the weight of this balanced cut, the weight of the edges crossing the cut, is at most 3 over 2n times the cost of the tree itself. And the proof is from the Dasgupta paper. You take the heavy light decomposition and you just cut a child or a subtree that has the desired balanced cut size. So the decoder is going to take this computed. No, it's actually supposed to be there. So the hierarchical clustering cost, it blows up the weights by up to n. So it's a sum of edge weights times the number, a number up to n, the size of the subtree.
Oh God.
So you need, yeah. Okay, so you now take the computed tree, with a balanced, you compute this balanced cut, which you can do easily of the tree. And now the decoder it only considers edges that cross the balanced cut. And it says for those subset of data points, just guess that there's 0. So that's a similar strategy for the minimum spanning tree. So in our example, it would know that the edge from B to C crosses this cut. So it guesses that guesses that the data point that was mapped there is a 0. So if the cost of the tree is, let's say, n squared over 100, which you would get by if your additive error is less than n squared over 100, then the cost is n squared over 100. Then the weight of this, by this lemma, the weight of the edges that cross from A to B is less than n over 50. So it means that in the reconstructed set I, the subset, there's at most n over 50 ones. And now we need to show, to come up with a contradiction, we need to show there's a lot of zeros, because if you had n over 50 zeros in I as well, that would be fine by the reconstruction lower bound. But if you had like n over 10 zeros, then you would be reconstructing too much of I. So we're going to show that there's like n over 10 zeros in the reconstructed set. And the way we do this is with one final observation. It's that the hierarchical clustering tree, it cannot distinguish those edges that were sampled and just happened to have a 0 in the data set from edges that were not sampled, because those not sampled edges also had weight 0. I didn't put that in the encoding, but they are encoded as a 0. So it cannot distinguish. So it cannot distinguish the green 0, basically, the edge with that has a green 0 on it and was sampled, from all of the other edges that were not sampled. So we have a conditional independence. The cut itself is conditionally independent of the sampled edges E prime that have a 0 on them, given the sampled edges E prime that have a 1. So in other words, the cuts cannot avoid the zeros. And that's exactly how we show that there are enough zeros in the cut. So the expected number of zeros crossing the cut AB is at least the size of the cut AB divided by 2D, because that was our sampling probability, times a half, because that's the probability of putting a 0 on that edge. So it's the size of the cut, the number of edges rather crossing the cut, divided by 4D. And now we have to make our other assumption. If you assume that this is an expander graph, a deregular expander graph, this is at least n over 9, or n. It's like linear. So that shows that there's enough zeros. So just a summary of our attack. We achieve a reconstruction rate contradiction for a deregular expander topology. If your additive error is less than n squared over 100, you know that there's not very many ones in the reconstructed set. And just due to randomness, there has to be a lot of zeros. So you will have a lower bound for something like for edge weight differential privacy. So the takeaway is that a sparse expander is just as hard as the complete graph. We showed the exact n squared over epsilon lower bound. Here I used epsilon being a constant, but you can use group privacy again to show it's n squared over epsilon. And also we know that approximate differential privacy won't help, because the previous lower bound only was pure differential privacy. Okay, so this is now a summary of our contributions. New lower bounds for minimum spanning tree, minimum weight perfect matching, hierarchical clustering. They show that complete tightness for hard topologies. And then they also generalized, not completely, but somewhat to classes of sparse graphs, such as any graph with a log min cut or sparse expanders. And some remaining questions from this work are topology-dependent lower bounds for minimum weight perfect matching. Can we tighten the hierarchical clustering upper and lower bounds? So can we see which is the log factor necessary? I think we really only scratched the surface with these embedding techniques. Can we come up with more interesting gadgets, simpler gadgets, or use random embeddings as we did for our hierarchical clustering that could just have some more fun random graph theory? And finally, yeah, there's a lot of other problems we can study in edge weight differential privacy as well. Okay, and great. So I'm just 1 minute over. Here are the references that I used, and thanks for your attention.
Questions? On the comment, or I'm passing along a comment I received about hierarchical clustering.
Yes.
So in bigger what like most lower bound instances of hierarchical clustering to say actually or expanders.
Hmm.
And then people who are looking at this lower people are people are too well.
Okay.
Look at it and say, but you never want to cluster an expander because expanders have the highest cost for hierarchical clustering.
Yeah.
They're completely unclusterable.
An expander looks like a complete graph, right?
Exactly.
In a lot of ways. Yeah.
There is no cluster structure.
Yes.
Do you think, like, now that you start looking at simplifying instances, one can even look at actually something that is clusterable? Like, it should be dense and still have a low cost. Like, the only reason for expander, the cost became low is because it doesn't have enough edges.
I think there might be multiple ways of looking at this question. So you could say that a road network, if the topology is a road network, that oftentimes is close to being an expander. But, or maybe not always, right?
No, expanders are linear. The expanders are as far as it is.
Okay, I see. It might be. I definitely think it's an interesting question, and I'm not sure like what graph family to look at. I imagine you're going to have to eventually use some form of expansion. Like it might, maybe the most interesting lower bound we could come up with would literally parameterize your thing by the expansion or the gap in the eigenvectors or eigenvalues. I definitely think like looking at planar graphs is like maybe not for hierarchical clustering because that's not. I feel like that algorithm is not very geometric somehow. It could be actually.
No, actually, sparse has been around for some time.
Oh, sure. Okay. Yeah, maybe. I think looking at planar graphs could just be interesting in general for all these problems.
Do you have a concrete open question here beside that minimum rate buffer junction?
Concrete open question is let's try and resolve. Can we resolve this hierarchical clustering upper bound and lower bound? It's a matter of a log factor, but I did think about it for some time and it was kind of interesting. I'm not completely, I think theoretically it might lead to something interesting.
But it's also very hard because you have to assume on the hardness of approximating a sparse plot. If a sparse plot can be approximated.
Oh, but let's give ourselves exponential time.
Wait, then what is the gap?
So the gap is just log n squared log n over epsilon. Additive. Yeah. So I think the exponential time one could still lead to something interesting.
That's longer.
Yes, but you have to I tried something with union bound, but you have to do there's too many hierarchical clusterings, and I tried to prune it, but I didn't know how to do it. I think that's kind of the way, like prune the set of good hierarchical clusterings. Kind of interesting.
Any other question? All right, that's time for